Okay, my name is Bernard Murphy. I work for MEI, and in some of my spare time I like to give masterclasses. And what we're going to talk about this evening is really the mathematics, or some of the mathematics behind dissections. I'll explain what dissections are in a moment. And there are, I think, lots of ideas that could be used, not just in masterclasses, but with students of all abilities. There are two kind of big mathematical ideas, and then lots of just interesting dissections, as I hope you will see. I won't go through this because I know the people in the room understand how to use this online classroom now. So the general idea of a dissection is you take one usually interesting shape, like an equilateral triangle, and with as few cuts as possible, try to turn it into another interesting shape. And you can see on the screen here, we've got a way of cutting up an equilateral triangle into only 4 pieces, which can form a square. And to actually prove it's a square is another question, but we can look at that later. So at the start of the masterclass, what I tend to do is when the students are arriving, they are given either these 2 diagrams at the left or the 2 diagrams at the right, and a pair of scissors, and they cut up the shapes and try and fit them into the empty shape, into the empty outline. And really trying to impress on them the fact that, who on earth thought of these particular dissections. They look very strange, but in the masterclass they'll find out where such things came from. I use a lot of Geogebra files, and all of these are available from Stephen Lee at the IMA after the talk this evening, and I'll show you some of them. So I'll start with the one that's which I have running on the screen as the students come into the masterclass, and this may take a few seconds to come up. Is that on your screen now? Can you see it all right? Yeah, okay, that's good. So I'll, rather than animate it, because that doesn't work well in this online classroom, I will do it using the slider bar slowly. And you see very satisfyingly it fits perfectly. And I have that on a constant loop. And yes, students can't fail. Well, I don't think students could fail to be impressed by that. Doing the Geogebra programming is interesting, of course, and I think at times I have got a bit carried away with it. And the appeal of the mathematics, to some extent, to me, is about being able to do it in Geogebra. So I've always got to rein myself back in and think this is a masterclass, it's what they're doing rather than what I've done that is important. Anyway, you'll see some more of those, and as I say, all of them are available from Stephen afterwards. Okay, so we start by looking at these 2 shapes and just again trying to get them to be impressed by the fact that somebody stumbled across a way of splitting the cross up in the left into 5 pieces to make the square. Very surprising result to my mind, and those students who seem to appreciate that this is surprising are the ones who get the most out of the class. So we'll go back to basics to begin with, and we start with a 6 by 6 square and a 4 by 9 rectangle. Now, of course, for dissection to happen, to be possible, the 2 shapes must have the same area. That goes without saying. So I'm going to set the timer for 30 seconds just to give you a chance to think about how you might split the rectangle into 2 pieces that will form the square. So only 1 cut is necessary, but it might not be a straight cut. Ah, Right, on cue. Well done. Now it will be very rare for any students, and typically it's year 9 students I do this masterclass with, for them to get it in under a couple of minutes, but eventually somebody does and everybody else is impressed, and sure enough, that's how you do it. As we show on the next screen, you can see how those two pieces would fit together. So that's, you know, accessible but not particularly interesting. So we then ratchet up one notch to this idea where you can take a regular hexagon, and I cut it into however many pieces there are there, 15 pieces is it, and those pieces form a 6, 12, it can't be, it must be 13. Those pieces can be split up to form 3 smaller regular hexagons. And again, there's a Geogebra file that does this, which you've got access to. I won't show it now, but that's how it works. It's interesting at this point to discuss with the students what the ratio is between the side length of a small hexagon, and they're all the same, and the side length of the big hexagon. And the fact it's 1 to root 3 is quite interesting, and can be, you can think of it purely in terms of ratios of areas and working backwards from there, or actually do some geometry. Now, in dissections, Greek crosses are very prominent. I don't know why, it's just I suppose that there are lots of interesting dissections that come from them. So a Greek cross, as you can see there, is made up of 5 congruent squares. There's a common dissection of splitting a square into 2 Greek crosses. In this case, the edge length in one are double the edge length in the other. And that's a way of doing it with 6 pieces. But I claim it can be done in 5 pieces, and they all get a few minutes to think about it. And naturally, nobody can do it. But then I drop some hints about start with the little Greek cross as a whole in the middle of the big square and think about symmetry. And then with that hint, it doesn't take people long to spot this one. That's quite pleasing. Okay, and then once we've done that, there's a lot more coming up on Greek crosses, but to try and break things up and get students thinking mathematically throughout, I then look at the problem of splitting 3 congruent squares, starting with 3 congruent squares and making 1 big square. And the construction lines show you what to do there. I think it's, in fact, let me bring up the Geogebra file for this one. So they all have compasses and straight edges and scissors, and first thing I do is start with compass point on B and radius BD. And now it's interesting to think why AW has got length the square root of 3, and why the square root of 3 is important in this dissection. Of course, if you put in 3 small squares to make 1 big square, then the ratio of the edge length must be 1 to root 3. So we need that length root 3, and we've now got it. It's length AW. So we can spin that round, AW, to get a length along the bottom edge. Let's call that AX. And then we're drawing that line, and that's going to be one of the lines that we cut along. Now we need to take that edge, that length AX, that root 3, and use it with compass point on E at that radius, and that allows us to get point Y. Okay, you might want to think about what happens if you haven't got collapsible compasses. Sorry, if you have got collapsible compasses, and how you might do it otherwise, but that's the general idea. And then if you drop a perpendicular, and again that's interesting, compass construction to drop a perpendicular, then you end up with these pieces. And there you can see that there are actually, it looks like there are 3 pieces, but since these were originally 3 separate squares, then there are actually 6 pieces. And the green piece slides down, as does the red. So again, not as attractive as some of the Geogebra files we see, but some real mathematical thinking going on there for the students to think about the importance of the square root of 3. Okay, now back to the Greek crosses. This tessellation of Greek crosses has similar properties to a tessellation of squares in the kind of the fourness around every point. Or if you think in terms of jewels, if you do a dot at the center of each Greek cross around a common point, then those centers can be connected to form a square, and that square will tessellate out. So on the basis of that, we can start to superimpose a tessellation of squares over this tessellation of Greek crosses, look through the top tessellation of squares to see the pieces you need to cut out underneath. So here's one example. Now, admittedly, this is not the squares from the centres of the Greek crosses you saw on the last screen, but it's a similar idea, as you can see. And if you look at the blue and red square, then those 5 pieces can be rearranged to make the yellow and red Greek cross, or vice versa. So there's a way of cutting a square into 5 pieces to make a Greek cross. Other examples, well, in this case here you can see that the square has got an area greater than the Greek cross. In fact, the area of the square is double the area of the Greek cross, and you can imagine that these squares would tessellate in the same way, and so the pieces inside the square form 2 Greek crosses. And it's easy to see the one on the left, how that works, and the one on the right, well, the 3 blue bits make up a Greek square, and then the white bits make up another Greek cross, and so do the white bits. So at this stage, the students have got a feeling for what's going on and how they can get a dissection of a square from a Greek cross and so on. And I'll give them the tessellation of Greek crosses you saw a moment ago, and they make their own up. And so they're looking to be more creative, to try things that they haven't seen me do. And the kind of things that they tend to come up with are like this. So the one on the left, we've got the 4 coloured pieces make a second Greek cross, and of course there's the complete Greek cross in the middle. And the one on the right, those pieces make a single Greek cross. And let's have a look at that one, or those 2 on Geogebra. So the one on the left, first of all, you can see that those 4 pieces do in fact make another Greek cross. And similarly the one on the right. There's another Greek cross. And again, you know, I think you might be able to see that I got a bit carried away with being able to do this in Geogebra, so it's always thinking about what the students can do rather than try to impress them with these files. Okay, a similar idea of superimposing one tessellation on top of another is given here. So the blue tessellation on the left, again that's got that similar recurring pattern to squares. And so if the red square has got area equal to the sum of the 2 sides of the blue squares, then looking through the tessellation of red squares, you can see how you can dissect that big square to make the 2 smaller ones. A more appealing one is with this semi-regular tessellation. The little red squares that you can see are the same size as the little black squares. So what this amounts to is that the remaining pieces are going to turn a square into an octagon. And again, to see how that works, That's the end of it. Let's start again. So you can imagine that the white square, which is part of the dissection, of course, just forms the other square, and those 4 pieces form the rest of the octagon. So we've got, obviously it's 5 pieces. The 5 pieces in the square. Sorry about that. The 5 pieces in the square, which includes the little square, of course, together make the regular octagon. And it will be interesting to try and find other examples. I've just given three there, where you've got ways of turning squares into other shapes, but I'm sure there's lots more out there. Now, one of the more mathematically interesting aspects of the masterclass is this. It's kind of a one-off. It's not one tessellation superimposed on another, and it's not the second big idea, which I'm going to come across in a moment. But it's a compass construction of how you can turn a regular hexagon into an equilateral triangle. And I think it's mathematically interesting when you try to prove that those 6 pieces do genuinely form an equilateral triangle. And before I show you where the difficulty is there, I'll run through the individual steps. So here's the regular hexagon, and point C is, as you would expect, these 2 lines are perpendicular and they pass through these 2 corners of the regular hexagon. So the first thing I do is connect those 2 corners, easy enough, and then drawing that line there. Then do this quarter circle, which determines the point B. And then on AB, you don't make a cut along AB, but on AB you form an equilateral triangle. So ABD is an equilateral triangle, but you don't cut out AB. Then this is the interesting bit, that you draw a line which starts at this intersection point here, goes through the corner of the equilateral triangle, and hits the top edge somewhere. And what you've got there now is 6 pieces that can form an equilateral triangle. Those are your 6 pieces, and that's what the equilateral triangle looks like. There is an animation of this available from Stephen. I won't show it now. But are we sure that is equilateral? Now, by construction, this angle in the top of the equilateral triangle is, of course, 60 degrees, but it's not obvious to me that the angles next to it are both 60. And so what I'm really saying there is it's not obvious to me that this final line that we drew in is parallel to the line segment AB. And I haven't found an easy way of proving that the resulting shape is genuinely equilateral. Now, of course, you can't do this by chasing angles, because the way that this final line was constructed depends on lengths as well as angles. So you're going to need something that's reasonably sophisticated, and the only way I've managed to do it has been using vectors and cosine rule and things like that. It feels to me as if there should be a simpler way of doing it, and again, for certain audiences, that's the right kind of question to be asking. Perhaps not for year 9s. Now, the 2 big ideas. One is one tessellation on top of another, looking through it and cutting it out, and that opens up a whole world of dissections. The other is to do with strips. You take your 2 shapes that are the same area. So here I've taken a regular hexagon and a square. They must have the same area for a dissection, of course. Now, what I'm going to try and do is form a strip from the regular hexagon, based on the regular hexagon, and a strip based on the square. Now, to form a strip, an infinite strip from the regular hexagon, I draw a line across the middle of the regular hexagon, and then rotate the top round. So you can see that the regular hexagon is actually made up of this, this trapezium and this one. And then I take an infinite strip of those. Well, it doesn't have to be infinite, of course, but I need a few of them because I'm going to do some overlapping. Then I take a strip of squares. And now the crucial thing is you've got to tilt the strip of squares at an angle, at a particular angle. Now I've drawn in 3 of the squares in the strip, and you'll notice that this rightmost square has got one corner on the bottom of the strip of trapezia, and the next corner is on the top row, on the top side. Now what this means then is that the area of overlap, and that's the pieces I've numbered 1, 2, 3, 4, 5, have the same area as the square, and also because they've got the same area of the square, they must have the same area as a hexagon. And if you think about the parallelogram, the parallelogram made up of 1, 2, 3, 4, 5, those strips have got the same base as the square and the same perpendicular height as the square, and therefore the same area. And by cutting out those pieces, as I've done there, then you can see how they fit into the 2 shapes. Now, here I stuck with these corners being on the top and bottom of the trapezia. But all I needed to do was make sure that my strip of squares was inclined at that angle to the trapezia. Because once they're at that angle, I can slide my squares up and down. So I don't need, once I've determined my angle, I don't need to keep a corner here. I could have moved it up slightly. And in doing so, I might get a dissection that involves fewer than 5 pieces. So this adjacent corners idea just determines the angle between the 2 strips. You are then free to slide your squares up and down in between. And of course your trapezia left and right. So that's one example. Another example uses a Latin cross rather than a Greek cross. A Latin cross, which is made up of 6 congruent squares, if I chop the bottom half of it off here and put it up at the top right, up here effectively, then that can carry on left and right to make a strip. So I've done the same thing. The square has got the same area as the Latin cross. I've taken, in this case you can see that adjacent corners of my square lie on the top and bottom lines. And then I've got my infinite strip of squares, and I could slide squares up and down if I wanted to, fixed at that angle, but after playing around with it for a while, it seems to me that positioning the square exactly as it is gives you a minimal dissection into, in this case, 5 pieces again. And that's what the diagram was that we had at the start of the session, which, students are thinking, how on earth did anybody find out where to make these cuts? Well, that's what they do. Now, the problem we hit next is, this is all well and good, but if you want to start with 2 interesting shapes, a square and something else, for example, then it's very difficult to find other shapes that you can easily make such a strip with. For example, a pentagon, it's not at all obvious what you can do to a pentagon to turn it into a shape like a parallelogram, for example, that will form an infinite strip. But the pentagon actually gives an interesting dissection in itself to do this. So let's have a look at that one. Okay, so the idea with the pentagon is you chop off the top triangle that you can see there, rotate it around to the side. So of course at the moment what the resultant shape is not a parallelogram, but you can then take the midpoint of that rightmost edge and draw a line through it that is parallel to the left hand edge of the original pentagon, and then chop that bit off and put it down there. And what you're left with is a parallelogram that you can then use as part of your infinite strip. The problem, of course, is that already, before we've even started, the pentagon's in 3 bits. And if we're hoping for a nice dissection with squares, a strip of squares running across this, well, the chances are we're going to need a lot of pieces because we're starting with 3 to begin with, before we've even thought about the squares. Nevertheless, we persevere with this. And if we do, we get the dissection you see at the bottom. 6 pieces, it's not too bad. Again, it turned out, after playing around with it for a while, that that position was the best. Of course, I haven't really emphasized how moving the strip of pentagons left and right will change things, so I chose my point here at the top, where the corner of the square met the top of the strip, as being a corner of the original pentagon. And there are the 6 pieces. Not at all pleasing, to my eye at least, because of we've got some tiny pieces in there and some big pieces, but still interesting, I think. Just one more of these. Actually, no, there's a couple more. A regular octagon. Now, I think you play around with the regular octagon for a while, and it is difficult to turn it into a strip, but this is a very nice way of doing it. These 2 edges here are parallel to the bottom edges of the octagon, and if you then bring the red piece below the blue piece of the octagon, well, you can see it at the bottom, spin the green rhombus round, and you get these 3 pieces, which again can make this infinite strip. Tilting your squares at the right angle, and when I'd done it, I found this was a good point for the square to meet the bottom edge, kind of predictable. Then what you're left with is, oh, there's a GeoGebra file for that. Well, I won't show it, but you can see that there is a way of doing that. I say I won't do it. I don't think I've got it lined up ready to do. Let me just double check. No, I haven't. I haven't got it lined up, so again, it's available from Stephen. But there's another one. And as I've said a couple of times, I've got carried away with GeoGebra a few times in dissections. So here's another one. I was thinking, what other shapes could anybody possibly be interested in? So there's everybody's favourite right angle triangle and an equilateral triangle, and that takes about 9 pieces, I think it is. No, 7. 7 pieces, but not particularly appealing. And then, of course, the equilateral triangle and the square. Now, the thing to notice about this, well, first of all, notice how I've split the equilateral triangle up into a shape I can make the strip out of by chopping off the top bit and putting it down here. So it's into 2 pieces already. And then I put the squares across, and you will notice here that I've actually taken the trouble of sliding the squares up a bit. So it's not obvious just by looking at this that those squares are at the right angle. But I originally put them at the right angle by making sure that, for example, this corner was on the top edge and this corner was on the bottom edge. But in doing that, the dissection I got used up more than 5 pieces. So I shuffled it. I started doing some sliding, and it seemed to me that this was the best way of doing it. Certainly the most visually appealing, because it uses 5 shapes that are all a decent size. Now, notice here that in the equilateral triangle, the green and the purple are adjacent, and they are in the square as well. So actually what we've got is a way of splitting one of these shapes into only 4 pieces to make the other, rather than 5. Because the green and the blue could actually both be coloured green. It's from this, you need to do some thinking, but you can see when you put them back into the 2 shapes that is in fact the case. And that brings us back to the animation that I show at the start of the masterclasses, they're all coming in, which is how these 4 pieces, green and purple together, can form this piece here. And we can do that by a ruler and compass construction. So rather than resorting to these 2 strips, there is a way of doing this. And my final Geogebra file shows how to do that. And at this stage in the class, they're all following it step by step. So let's have a look at this last one. So we start by finding the midpoints of 2 adjacent sides, and that's a compass construction, of course, rather than measuring it, going halfway along or folding it. We're purists at this stage. Draw the circle centre D through C, and extend line AD so it meets the circle at a point we'll call F. Then find the midpoint of AF and call that G, and draw the circle through centre G through F. Nobody is expected to be able to see where this is going or why these things work. That's an activity for us as tutors rather than the students, I suggest. So we extend side BC so it meets that circle at H. And I haven't put the instruction here, but this is a circle centered on D through H, and it meets the bottom edge AB at J. Connect JD. That's going to be one of the 4. That's going to be one of the cuts that you make, and then take that length CD and form a similar length JK on the bottom edge. Again, there's an issue here with collapsible compasses and so on, but it's all possible. And CD, of course, is only is half the edge length of the triangle, so there are other ways of doing that. Then K, you drop a perpendicular. Drop a perpendicular to JD. Call that R, and again, it's compass construction in there. And I was pleasantly surprised by how many students wanted to do the right thing and do the compass construction rather than just say, oh, it looks like a right angle. Similarly, a perpendicular from E through to DJ, and there you have your 4 pieces. Proving that that forms a square is a different problem altogether. But there's a compass construction which gives the same which can give the same pieces as the 2 strips, as long as the strips are at the right angle and so on. Okay, so that's the general ideas that I use in the masterclass, and this session tonight has all been about ideas for a masterclass. I don't want to pretend that this is the polished product, because it isn't. I did find that it really needs students to be actively involved. Now, I happen to be doing this class again on Saturday at the Museum of Science and Industry in Manchester. And what we're going to be doing there is getting students to make some of these as large as possible, and we'll be marking them for accuracy. So doing them on a huge piece, having done a small compass construction, make it much bigger on sugar paper, and we might have races, students sitting either side of a double-sided whiteboard. One side can't see the other, and they're having to do the tessellations with the pieces themselves. So there are other ways of getting students more involved, but I think mathematically there's a lot of rich ideas in this session. So I'll stop there and I'll hand over to Stephen if you want to say anything or ask any questions, and same for you, Alan.
Yes, I was just going to ask if there were any questions for Bernard at this point. Although I don't think people can use the mics, but you can type into the box.
Yeah, how do you come up with a compass? Well, I don't. It's the short answer. Some of these compass constructions are classics. I don't know. I don't know the answer to that. Maybe it's kind of working backwards, thinking what the results have to be, and then deciding how on earth you can form these pieces. So on this last one, I don't know. The first time I saw it, it's like the first time I saw the origami bird that flaps its wings. I thought, how was anybody creative enough to see that? Clearly, when it's the three squares forming the big square, well, that's doable, and ones at that level are. But I think the compass construction here, and also the one for turning the regular hexagon into the equilateral triangle, I don't know. Other than you start with a regular hexagon, you know what the side lengths of the equilateral triangle have got to be, and so you can try and find those lengths by geometry and then turn that into compass constructions. But beyond that, I don't know. I've not actually sat down and tried to find one for myself, so I just assume it's extremely difficult.
It's probably worth saying that if people are interested in this kind of construction and finding the right constructions, then there is an app available which you have to pay for, called Euclid, and that forms, as you'd suspect, the basic Euclid geometry ideas, and you build up different things, shapes and angles and things like that in that app. I think it was something like 69 pence, but anyone who's interested in this kind of thing would really like that, I think, in order to have a play around with such a thing.
Yeah, it's a great app, and I think there are about 30 puzzles in there before you finish, and 69 pence, it's probably about 69 hours I've been working on it, and 29 of the 30 seem doable. The 28th, or the second last one, if there are not 30, I still haven't been able to do, and I'm reassured that I found other people who found that one very difficult as well, but it is great fun. The classic text used to be, and I believe still is, on this topic, it's called Geometric Dissections, and it's by, I've got it here in front of me, it's by Harry Lindgren. My copy is dated 1964, and I managed to find it on a books or eBay or somewhere. But yeah, it's a great book, goes into a lot more detail than this. This is really only the first couple of chapters, but lots of ideas there if you can get hold of a copy of that.
Okay, I think we're probably just about there, unless there are any final questions. I see there's the typing in the box. Yeah, Alan, if you want to contact me, then I'll make all of the files available to anyone who requests it, and you can get me on the email stephen.lee@mei.org.uk, which is just on the screen there.
And the PowerPoint as well, of course.
Yes, and the PowerPoint. So just to say, this talk was an IMA branch talk for a virtual environment, and that Bernard, who's part of MEI like I am, have put this together, and you'll hopefully be able to watch this back on a video shortly as well. So I'd obviously like to thank Bernard for doing the talk, and MEI for hosting the event as such. And I think that's all, so thanks for coming, everyone.